For our group project, we devised 3 algorithms for a multi-story building. These algorithms were lift control systems. Each algorithm behaves in a unique way to attempt to maximize the efficiency of the lift when it comes to taking in new people, moving between floors and delivering them to their requested destinations. The algorithms are also designed to accommodate new floor requests as it runs. To accomplish this task, we utilized a variety of primitive and abstract data types, such as lists, dictionaries, queues, and priority queues with heaps. To begin with, we designed the format of a JSON file that would store all of the properties of the described multi-story building. These properties include the number of floors, the lift capacity, the requests made by people on each floor, if any, a Boolean value signifying whether the file could be written to or not, and finally a list of weights for each floor, which dictated their popularity, hence their probability of having a new request added to it post-creation. The create building procedure takes this information as parameters and adds them to a dictionary called data, before writing it to a JSON file with a specified name. It then generates the floor requests in a dictionary of lists, with one list assigned to every floor. Requests are represented by integer values that point to the specified destination. This is done in accordance with one of 2 building types. The standard building type just randomly assigns requests to random floors beneath a specified maximum number of requests per floor. The advanced building type utilizes the weights list to have floors significantly fluctuate in request amounts, with the reception always being busy. The add to building function takes 2 parameters, the file name so it can edit the building properties, along with the maximum request per floor to ensure that no floor goes over that number in request. The wait list is once again used to favor more popular floors, and a random floor request is added to the decided floors list in the floor requests part of the dictionary, after a check is made that it's different to the current floor that the request is being made on. So just to show how this works, we're going to print what it returns, which is the floor requests, with some test data, and we're going to use advanced. It should be noted that writable is always default set to true, and this is what is output. You can see that every floor is also within its own list. That's to work with one of the algorithms better, and consistently, because we're using the advanced type, the reception is always busier, but you can see it varies every time we run it. Now we're going to print the results of the add to building function with the same file name and maximum request of 10, and this is what's output. So this is not the same recording, so create building made a different base building to start off with, but if we run this again, we can see, it takes me a while to search for it, but we can see it's actually floor 7, which has had a new request for 4th floor added to it. And now in just a moment, I'll run it again after I've found it. And now I'm going to run it again, and after some searching, I believe it's floor 5 that's had a request added to it, and in the 3rd time, it's floor 6. Which has had a request.
So I was in charge of making the scan algorithm. So the scan algorithm starts at the bottom floor and goes up, checking each floor to see if there are any passengers that need dropping off the lift or picking up onto the lift. If there aren't any passengers, then it will skip the floor, and it will do this all the way up until the top floor, where it will change directions and go down the building. It will repeat this forever, and it can only change direction on the top floor or on the bottom floor. It can't change halfway through its journey. In terms of implementation of the scan algorithm, I split it into several subproblems. The first being dropping passengers off, which should be the first thing that the lift does. It does this by checking if there are any passengers in the lift that match the current floor. If so, it will drop them off onto that floor. Then it will check if there's anyone waiting on that floor to get on the lift. If there are, then it will take the number of people to fill the lift onto the lift. Then the lift needs to go to the next floor. This is done simply by incrementing the floor counter, and once incremented, checking if the lift has reached the top floor or gone past it, and then changing the direction so it's going down, so that you're now decrementing the floor counter. Then the floor number can be changed and the whole process starts again.
The look algorithm is like the scan algorithm, except When there is no more request in the direction that the lift is currently going, the lift will change direction. If there is someone waiting at the current floor that the lift is on and there is space in the lift, they will be let in. And anyone that was in the lift requesting the current floor will be let out. If the lift is travelling upwards, it will check each floor in turn to see if there was someone waiting for the lift. And then it will also check if there's anyone in the lift wanting to go to those floors above. If the lift is travelling down, it will check if there's anyone waiting on the floors below for the lift. And it will then check if there was anyone in the lift wanting to go to any of the floors below. If there is no one to pick up or drop off above or below, then the lift will stop at the current floor. And if the lift is travelling upwards and there is no one to pick up or drop off in the upwards direction, then the lift will change directions. The same will be done in reverse if the lift is travelling downwards. We then check that the lift isn't going to go outside of the range of the building, and if it will, then the lift changes direction. And then all of the updated variables are put into the JSON file. The myLift algorithm is based off the look algorithm, however it differs in a few ways. Firstly, floors are prioritized based on if there is someone already in the lift wanting to go to that floor. If the lift is traveling downwards and the requested floor is 1, and then it is prioritized based on which floor is the closest to the current floor, and also in the same direction as where the lift is currently going. This priority queue is done using a heap which organizes the requests into a binary tree. They are then added and removed from the lift in the same way as the look algorithm. If there is no one waiting above or below the lift and there is no one in the lift, then the lift will automatically park at the first floor. That is how the look and myLift algorithms work.
Main functions allows us to run individual algorithms. When you run it, it will ask you for input data, which it validates, and then you have to choose an algorithm to run. And it will run the algorithm, obviously, and it will return the results, so it's, where, like, people, which floor they've been sorted on, and how long it's taken. Some of the algorithms are marked as real time, and these algorithms essentially try to simulate the time it takes for the lift to actually change between floors, or stop at floors and have people cross between the floors and the lift. The real-time algorithm also runs infinitely, whereas the other algorithms just read from a file. The real-time algorithms will keep generating essentially new people going from floor to floor.
So this is just a recording of the main functions kind of algorithm working. So we're first presented with the building type, and I'm just going to test the validation here. So the try and accept picks up that erroneous data as a string, also data out of the boundaries, also invalid input. So I've selected the advanced and then just put in some test data for the floors, max requests and capacity, and now I'm running the scan algorithm. Now it's quite a lot that it outputs. Essentially what the scan algorithm outputs is the original state of the building before a change is made, the state of the lift, and then the lift after dropping off anyone on that floor. So you can see kind of the process of how that happens with the first floor here. We have all the first floor go into the lift, and then they get dropped off at their respective floors. You can see the contents of the lift as we go through varies incredibly, and then we have the completed passengers at the end. Of course, it's all going to be the same number for each floor. You can see there's 3 people who wanted to go to floor 2, so the corresponding list to 2 just has 3 2s in it. Now I believe we're going to run the main function again and try a different algorithm. So I'm going to select advanced again and put the exact same data in as beforehand. But this time I'm going to select scan real time. And what this does, it takes a moment, but this just incorporates the time module and makes use of time.sleep to space out the movement of the elevator to make it a bit more realistic. But as you can see, the exact same sort of process is happening. It's outputting the same sort of pieces of data. Of course, the algorithm... Actually, no, sorry, the algorithms are behaving exactly the same because they're both scan algorithms. But we'll now see how the look algorithm works. It's going to be looking the same, but of course the algorithms do behave differently as evidenced in the code, but this is what it outputs. Again, at the end, the completed passengers list. We of course have a completed passengers dictionary with every iteration as well, which shows how the floors are being filtered in, and then by the end, of course, they're all completed. So I'm now actually going to run the look real-time algorithm, and of course this is going to go on and on and on, so I've let it run for a very long time, and I'm just speeding up the footage now so you can see how it's running. You can see that the fact that they're coming in like this shows how time.sleep is working to simulate this, and you can also see the behavior of the lift a bit clearer when it's divided up into segments, when it waits between floors like this. I'm now going to be doing the MyLift algorithm, actually with a little bit smaller input data this time, still on the advanced building type, but I've put in 5s instead of 10s. This way you can definitely see how the algorithm gets shorter, of course, when you use less floors to the building. But of course, 10 is already a lot, but you can go much higher than that. Now I'm actually going to call the real-time MyLift algorithm with the standard building type, just so you can see that that works. Once again, I've sped up the footage, but you can see that for every algorithm, it's outputting the same data. It's just the way in which the lift organizes these requests, which is different.
We created 9 unique scenarios, such as an apartment building during a morning commute, a male lift in an office building, and a lift in a car park. This was to measure the real-world effectiveness of each of the 3 algorithms. Each scenario has 3 height variations: small, 3 floors; medium, 7 floors; and large, 10 floors. Each of those variations had 3 variants with different lift capacities: 2, 4, and 6. This led to a total of 81 tests for each algorithm. These scenarios are represented as JSON files with requests from appropriate floors. To test each algorithm, we created a test file with intentions of running each scenario variant for each algorithm, sorting the data into a dataset represented by a 2D array that is then processed and fed into a graphing script so we can more easily compare the results of each algorithm. In practice, for every file in the scenarios folder, all the data is read, the new capacity is assigned, and then each algorithm is run for the scenario. The name of the file capacity and all data to be compared is written to an algorithm-specific dataset and is then returned in order to be used by the graphing code. We wrote a script to create graphs with the testing datasets. It can create a bar graph and a line graph. To create a bar graph, the names of the 3 algorithms are used as labels in order to compare the overall efficiency of the algorithms side by side. The line graphs work in a similar way. However, the multiple data points for each algorithm being compared allows us to present a much more nuanced comparison so we can better evaluate the situational effectiveness of each algorithm.
There are also the graph functions, which essentially just allows you to input data and then it will save that as a graph in the graphs folder. These graphs allow us to compare the different algorithms and also allow us to compare as the number of people increase, how does the time it takes for those people to essentially be sorted increase as well? Does one algorithm grow quicker than the other one? From the graphs, we'll be able to tell.
So for my final screen recording, I'll just be quickly showing how the testing algorithm works. So when we run it, you can see it's going through all of the many preset scenarios that we have. It's going to take a really long time to do that, but then we can feed this data, we do feed this data to the graphing functions. So from this graph we can derive that the average number of floors needed to traverse for each algorithm is kind of similar for the scan and look, but significantly lower for the MyLift algorithm. We also know that the average time for each person to move to their floor is significantly larger in the MyLift algorithm. We can also see with the line graphs that we can denote that the MyLift algorithm grows significantly faster than the other 2 algorithms.
We created a specification document to outline the key features and objectives of the project. The document contains a detailed explanation of all algorithms, scenarios, and data types, as well as all graphs produced by the testing data.